So everybody okay on syncing and sourcing? Yes, no?
I'm getting there.
And this is, if you remember, so we start off with what we call a ladder diagram, right? And generically we call this L1 and generically we call this L2. And then we draw circuits between L1 and L2. Okay. Now AC means nothing because AC has no polarity because it's what? It has constantly swapping. But DC has a polarity, right? I understand. So if I was to come over here and just do it, just one little push button, and then I come over here and put a light bulb. Now which one's plus and which one's minus? Huh? Either one. Okay. So if I come over here and make this plus on DC, I make this minus, then all my input devices, its common is the plus. All my output devices, its common is the minus. So when you hear the term common, most people think that to be the negative side because you're thinking about your car, right? You understand? But the common in electronics could either be a positive or it could be a negative. So if we use a positive as a common, we call this sourcing. And if we use a negative as a common, we call this syncing. But I could just as easy as what? Yeah, I could make this negative positive. Now this is no longer sourcing. This is what? Syncing. And now this over here is what? Now when we get to PLCs have to be, the input modules or the inputs and the outputs have to be powered up. Okay. So what that means is if I come over here and basically do the way we would connect the PLC. So what I would do is I would take my input device, no matter what it is, and we got all types of input devices, I'm going to put it right there. But now what it's going to do, it's going to connect to a port on a PLC. Single bit port. Now, if this right here is positive, I've got to get current flow. So if this right here is positive, now my PLC over on the other side, this is going to be the output. So this is input. And this over here is output. And then I'm going to come over here, I'm going to connect an output device right there. Here we're just using labels. Okay. Now if this is plus, then this input device is called sourcing. But the PLC's got to supply the what? To get current flow, what do we have? But current in DC, if we got a positive to get current flow, I've got to have a what? Negative. Okay, so this guy over here, inside on the PLC, this would be connected to a negative. So now I've got current flow. So what we're saying, if my input devices are sourcing, then the input port has got to be connected to the syncing. And this is the way our PLCs are connected, by the way, if they're on DC. Now this over here, my output device is syncing, so the port has got to be what? Sourcing. So inside the PLC, this circuit is connected to the plus, and over here, this would be connected to the minus if that's the way we go, but I could have just as well swapped it around. So if I'm using syncing input devices, then my port has got to be sourcing, right? You understand? If I'm using sourcing, if I'm using syncing input, if I'm using syncing output devices, then my port has got to be sourcing. Now, these PLCs, the 1100, allows me to decide. So when I come over here and look at, y'all can come up here, come on up. So sourcing and syncing only comes into play with DC. If I've got AC input modules, you don't care, right? So this would be the input module. Then what we would have is we'd have a bunch of screws on it. So this module over here would have 16 of them because it's 16. These guys run. Allen Bradley runs in words, and what's a word? 16 bits, right? Okay. And I don't have enough, so I'm gonna come up here and call this a common. So what I would do if I'm coming over here and my inputs I'm just going to put push buttons right here. So what would this be? So I've got the minus pointing toward the common on the module. I've got the plus pointing toward my input devices. So how is this connected? Well, but the input devices they're using a positive common, so these guys are all what? Sourcing. And then the negative is pointing to the common on my module, so these modules are what? And all I would have to do is just swap the battery around. And my output devices are the same way. So I got an output module. I'm going to have a bunch of screws on it. And then on this one of them is marked common. And this is where my output devices would connect. I'm just going to do one. So what would be the common here? If I'm sourcing, if I'm using syncing output devices, then how would I hook up my DC source? These guys are going to be, I want these to be syncing, so I want this guy to be minus. So the battery, or DC source would be hooked that way. This is a symbol, by the way, of a DC source. That could be a battery. Most people say it's a symbol for a battery, but it's a DC source. This guy right here would use the same symbol, but it would have an arrow through it right there. Anytime you see an arrow drawn through an electronic device, it means it's variable.
But the little line means that
the negative side.
So
yeah, the small line is the negative side of the DC source, and then the long line is the positive side. Now, normally each one of those lines are supposed to represent a cell. Yeah, but normally on a PLC. Yeah. That's the way it goes, guys. So that's the way you can actually see. Oops, I just lost my comment. I don't know. I think I got it screwed up. Now I've got this hooked up to the minus. So this is, so the PLC is syncing. So my input devices would be a sourcing. And then down here on the output, this guy uses relay outputs. And what's nice about relay outputs don't care if you put AC or DC on. In fact, if this guy here will focus. Might have to get my other camera. But this guy's got a common. It says relay output, and each one of the commons says DC or AC. So I established a common on these, and notice I've got this guy here jumped all the way down. So here every output port has its own common. and it's a relay output. So relay outputs mean that I can put AC down here, I could put DC down there, and then we would have to look and see what the contacts are rated at. So contacts are rated in two things. What's the two things contacts are rated in? Fuses are rated in two things. Just about all our electronic devices or electrical devices is usually rated in, got two ratings, right? Of course, resistors have three. What's the three ratings for a resistor? When we say size, ohms. Yeah, because you can't just say size because you got physical sizes so it's in ohms, right? What else? Watts and tolerance, right? Understand? Well, switches are rated in two things. If you ever went out and bought a light switch, it says it's rated, if depends, it's usually rated like 15 amps, and then it's rated at the amount of voltage that it can block, right? You understand that? So when a switch breaks, it's trying to break a push. And if it arcs too much, it'll arc over. So switches and fuses are rated in not only the current that they can handle, but also the voltage that the push they can guarantee they can break. I still can't get this to focus in, but that says common. It says AC/DC, AC/DC, AC/DC. So this is the plus coming up. So what I'm doing is I've got my outputs hooked up as sourcing. So all my ports down here are going to be set up to sync, right? You understand that? Are they going to source here and what I'm going to hook up to the sync? Will that help you, Gary? Any more questions about what was on the review? Huh? Could they? With what? Practice on the test. I think I told y'all that binary math, the binary division, that binary math is not going to be on the test for this class. It's just covered in the book.
Well,
You don't even say,
and all that.
we borrow too. It's just like in base 10, people don't borrow. You say you borrow a 1, but you're not borrowing a 1, you're borrowing a 10, right? You understand that? So what you're doing, if you've got 5, 6, 7, 8, and I come over here and do 4, 8, 7, 3, right? You understand? You start off here, right? What would you do? This would be 5, this would be 0. Well, I got to borrow, but I'm going to borrow a power of 10. And most people just come up here and put that. Well, that makes it 16, right? You understand that? So what you're doing is every time you borrow from the previous base, you're borrowing a what? A 10. So in binary, you're borrowing a what? A 2. Every time you borrow 2. And then if this right here was 8, then I would drop this down and make it 15, and I would come over here and borrow a 10 that way, right? You understand? Well, when I borrow on base 2, and I have a 2, I drop it back to a 1, and I'm borrowing a 2. So on base 2, you borrow 2. And when you carry a 10 in base 2, on base 10, you carry your 10 every time you put a 1 over there. So in base 2, we borrow we carry a 2, right? Or put a.
I think that's when you add like 4 or 5 numbers.
Yeah, you just.
But we're not going to have it on the test.
It's not even on the review, is it?
No. Yes. Oh, I don't know.
Binary math is not on the review, was it? Y'all understand why we call this a ladder diagram? Y'all understand why we call them rungs? Huh?
Oh, yeah,
I was going to draw a ladder for you. Thank you for saving me from that. So what we do is we start off on L1 and then we're moving toward L2. So the loads hook up to L2. I'm just using light bulbs. And then all my control devices hook up between L1 and the load, right? Always. And what we can do, guys, is we can hook control devices up in parallel. We can hook them up in series, or we can hook up in series parallel. And that's not what determines if a circuit is a parallel circuit or a series circuit. What determines if it's a parallel circuit or a series circuit? How the loads are connected. It's nothing to do with the control devices. It's how the loads are connected. That's what determines if it's a series circuit or parallel circuit. It has nothing to do with the way you connect your switches. No. What we don't have in motor controls, and we don't have this in PLC, in this PLC, is we'll never do this. We'll never have multiple loads on the same line. Now, so what we do, each horizontal, we call this a line. So this run would consist of 3 lines, because this line should line up with this line. So the rule is we can have one or more load per rung. We can only have one load per line. That's the rule. So a rung's got to have at least one load, right? You understand? There's no such thing as multi-load series circuits. And that's true on relay logic too. So this right here would be one rung, but it would be 3 lines, because this guy should line up with that guy right there. And this is true on our programming too. But what's nice is that if you try to put 2 rungs if you try to put 2 loads on the same line, what's going to happen is the application is going to say you got an error. So it checks on you sometime, like spell check does, right? So you spell the word wrong. Usually it does what? It lets you know that.
Oh, I printed that out.
Oh, you did the roads?
I did
No.
memory, but
The test is primarily on computers. Since we didn't get to the numbering systems, we're kind of shifting the numbering system over to the next test.
I kind of perused it, but I should have known.
That'd be nice to test that had all the answers. Right? So these are the rules for ladder logic. We're basically looking at the second page, the back, which is the rules for what? This is the rules for PLC programming. You'll need to, what does it say? So what does the first rule say? Control devices are going to be placed between what? L1 and the rungs loads. What does rule 2 say?
like small motors and serial motors.
Okay, flip it over. So we're close. They're saying. So what we're doing is I gave y'all both the rules of relay logic and also for PLC programming. So it should be a big highlighted at the top. Should see rules for PLC programming. These are revised for the ones that's in the textbook. Textbook guy's got a few little problems, but he does a pretty good job. So what did the first rule for PLC programming say? Should be the same thing, right? Okay, then rule 2 says what? Nobody's going to read that?
Run control devices.
Okay, so here's my output devices. They're placed between the what? The control devices in L2. What else? What's the third rule? Yeah, and that's a rule, but the problem is that your programming language is your application is going to take care of that for you. It's not going to let you place any input device vertically. What's rule 4? Nobody want to read that?
Errors that were not clear until corrected.
No, that's not the rule. That's the
With RS Logic 500 that runs output instructions must not be placed in series with other outputs.
Yeah, so there's no such thing as multi-element series circuits or multi-load series circuits in this. Now we're not teaching RS Logic 5000, so just these rules right here. Now RS Logic 5000 even. So what's the next rule?
Program flows.
Yeah, so what we don't want to do is we don't want to send stuff going back to left to right. It's going to be, so program flow is when the PLC starts figuring this out, it's going to do what? It's going to read your inputs first. And then what we're going to do on our PLC so we're going to take input devices. I'm just going to put, that's a contact. And then we're going to run through and then we'll go to output. So basically what the program does, it comes up, what the application does, it comes up here and scans the input, right? Runs through the logic of our program and then generates what? Output. That makes sense? And that's what it's saying. So the flow's got to be from left to right. All right, what's the next row? Go ahead and read one. Yeah. Yeah, so what happens is that every time we start a new rung, it's automatically going to put a rung number over here for us. What's going to happen on RS Logics, it's going to automatically put a rung in here. And it's going to be in. And it'll start off at 0, and every time you insert a rung, it's going to start numbering from 0. Okay? So rung numbers are automatically going to be inserted on the side over here for us. We don't have to do that.
The wrong number start with 0.
Yeah. Now, what you have to learn in computers, we don't start counting at 1. We start counting at 0. Because these are actually addresses inside memory. And what I tell my people, every once in a while you see a football player with the number 0. It doesn't mean that football player doesn't exist. That's just an address, right? That we could, when they're up in the booth, they say they can recognize the person's name. Okay, what's the next row?
User defined, not automatic
Each input or output device instructs logic address or simple name is entered above each instruction symbol. This location is predefined by the Ladder Logic PLC programming application. Note that related to RS Logic 500,
5,000, I think. You know, say 5,000. Keep it.
5,000, once a logical address for a bit instruction
I'm sorry.
is entered at the top of the symbol. The bit address is displayed below the symbol. A block input or output instructions logical address is entered at a predefined location inside the device symbol. RS Logic 5000 uses tags assigned to each logical address.
And we're going to learn how to use something called symbols, guys, instead of tags. So originally it was called symbols, and originally it was optional whether you assign a symbol or not. But in now PLCs, they're required, and they're no longer called symbols; they're called tags. Okay. Any more? Yes. No. Whose turn is it? Who hadn't read one?
Optional comment should be added in each instruction, symbol and wrong. RS Logic 5000, comment, distributed.
Okay, any more comments? And I'll show you all a basic program here in a minute. Because what we're trying to do is, and I learned in programming a long time ago that comments are critical in programming. Because what happens when you're writing a program and then you put it aside, then you come back next year and you figure out what in the world did I do that for? Unless you comment that. So comments makes programs a lot easier to follow. Comments are optional, even on most other PLC language. Any more? And so this is what we're dealing with. This is RS Logics. Hopefully I got my, well, this is just RS Logics 500. Of course, they got a new version out there called 5000, but this is still probably the predominant language out there, so there's so many of these PLCs running. Now, once we load this up, and then I'll show y'all some stuff. This is already going to be done for y'all. First thing we need to do is we need to establish communication with the PLC. So this is also true on the 5000s. They provide a program called RS Links. And then this is where, so what's a driver? Huh? Yeah, it's a piece of software specifically designed to run a peripheral, a device. And of course, this is all the drivers this guy here supports as far as communicating with other PLCs, other CPUs. We're using one called DH485, which is called the data highway, and it's already running. So that would be the first thing I would do. And then I could come up here and see who's active. And this is my MicroLogic 1100 PLC. So I've got communication established with my PLC. Then what I would do is I'd open up the actual application. So I'll find it. It's behind me. And then I could come up here to comms and I say, okay, who's active online? And what's going to happen is all the PLCs that you have out there should pop up on this list. We've only got one out there. And there it is. And we'll say, okay, and I'm going to cancel this because I don't want to create another problem. Then next thing we would do is we would come up here, we want to write a program. I'll come up here to files and now I'll go to new. And then the next thing I'm going to have to do is this application can program a bunch of different CPUs. So the first thing it's going to ask you is what CPU are we going to be programming? And where would this information be at? Usually there's a label on the side of the CPU, on the side of the unit that tells you what this is. If you was looking at this guy, it's got a CPU with slot 0. This information is on the little flat board right here. If I could program this CPU with this application, what I have hooked up here is it's a Micrologic 1100B. And the first thing it puts in there, it puts a rung in there for me automatically. And this rung is the what rung? Yeah, the N rung. It's automatically puts that N rung in there. You cannot put anything in the N rung. The N rung, it just tells it where the bottom of the program is. In the new version, they leave this out, by the way, because it's a. So what I'm going to do is, up here, this is our most often used symbols. And so what I'm going to do is I'm going to drag this guy down and I'm going to insert a rung. And it puts E up there telling me I've got an error. Why do I have an error? Yeah, well, one thing, I got a break short between L1 and L2, right? Understand that is bad. So what I would do is I would start hooking up, bringing in devices. So this is that's a normally open contact. And then what it's looking for me to address this to one of my input modules, or my input ports. Okay. Everybody okay so far? Any questions? Okay, pretty easy so far, right? So when I look at my inputs, I got I0, I/1, I/2, I/3, I/4. Then I got I/5, 6, 7, 8, and 9. So this guy's got 10 input ports, single bit input ports. And I have to tell it which one I want to use. So we start off by typing in I, which says I'm dealing with a what? Input. And then what we do is we put a colon. This is our separator between this is our separator between what type of port I'm going to, and then we start giving it the address. This is in module 0, so what comes next is module 0. And then what we put a dot, and then we would put a word number, and then we put a slash, and then we put a bit. Now, the problem is the word number depends on the module. If the module does not have multiple words on it, then the word number is optional. You don't have to put it in there. Understand? But we can buy an input module with up to 32 bits on there. And this thing in RS Logic goes in words or goes in 16 bits. So if I've got an input module that's got multiple words on it, then I would have to use the word address. If it don't have multiple words on it, then we don't have to put the word address in. Yeah, we'll come up here. So on ours, this is what we'll do. We'll come up here. We'll put N, then we'll put what? 0, then slash, and then we put a bit number. Okay, we're okay. Everybody okay? This makes sense. Then I'm going to come over here and hit enter. And what it's going to ask me for by default, it's going to ask me for a comment. And then it's going to ask me for a symbol. So comments go above it, and then the symbol is in green, right? Everybody follow me so far, but I still got an arrow. In fact, the arrow will be there until we check it. Then I'm going to put another switch down here. I've already used it. And you can use the same address multiple times, guys, but it wouldn't do much sense for me to put the same switch twice, right? So if I'm in a push button, then if it's got the same name, then it would have multiple contacts on it. This is all software, so we can simulate as many contacts as we want to. So I'll start off what? N, right? Then I put a colon. Then I put a, by the way, it shows me the next one available if I'm going by that. But let's go ahead and do all that. Module 0, right? Everybody okay? Then bit 1. I'm using module 0 because this isn't module 0 because this guy right here has those fixed into it. The first rung don't make any difference. I could come down here and I could insert another rung, and then I could come up here. So what we're doing, module 0 is kind of like your cell phone number. Your cell phone number don't change just because you're at home or you're here, right? You understand? So what I'm doing is I'm specifying one of these ports up here, one of these input ports up here. That's what I'm specifying. And these are internal, so the internal module numbers will always be 0. Now over here on this 500, since this is a modular PLC, then your address 0 is taken up by your CPU. It's slot 0. So if I wanted to address this input module right here, I would have to say 1. I would say I:1. If I wanted to output any of the 16 outputs on this guy, I would say I, right, :2. If there was a module here, this would be what? I:3, and it would be all the devices that are contained within that module. That make sense? So okay so far. So yeah, this is so I could come down here and I could put I:0/3 or 2, I'm sorry. And this is canceled, guys. You don't have to give it a symbol name. Right? You understand that? You don't have to do that. That is optional. But in newer PLCs, this has become known as tags, and tags are not optional. Because let me show you what I can do. So what I'm going to do is I'm going to bring another, I didn't want to do that. By the way, if you put something there you don't want, all you need to do is just highlight it and hit the delete key on your keyboard and it's gone. Okay. If I don't want it here, we can do, if I say, well, this is supposed to be in rung 1, you can just grab it and just move it. So we can drag just like we learned on our computers. Everybody understand that? How do you drag? Click on it, left mouse button, hold it down and move, right? Well, see up here, what I can use is I can come up here now and I'm going to type in start. And you see what it did? Well, it gave it the same address as my previous button. So this is what's nice about symbols, is that once you assign it, you can deal with it by name instead of dealing with it by address. It's just like in my phone. You got a contact list. And normally you don't, how many of you know all the phone numbers in your contact list? You don't, because normally you select them by what? By name. And that's a tag, right? In PLCs, that's a tag, but on this one, they don't call it a tag, they call it a symbol. So on this one, if I wanted to use this one again, I would have to remember, and I would give it a name, or I'd give it a symbol basically on something that it does. So I can come up here, I didn't assign this a symbol, so I'm going to come up here and I'm going to right click on it, and I'm going to put edit symbol, and I'm going to call it stop. So now I've given it a name that basically tells me what that push button's going to do, or that button's going to do. That makes sense so far? And then I'm going to over here and I'm going to grab this and I'm going to put, now notice, you can put these things over here, But now I'll always get an error. If I come up here and try to check it to see if it's okay, it'll always tell me it's got an error because I've got the load on the wrong side, right? You understand that? Huh? So here I've got a load. What do I need to do now? I need to assign it, gotta assign it an address. The address is what we gotta do. We can't assign it we can't assign it a name until we give it an address. Okay, so now I'm gonna deal with output. So I'm gonna come over here and put an O. It tells that I'm dealing with one of my output ports, right? You understand? And I'm gonna put a what? Colon. And then I'm gonna put a 0 because that's what the module numbers of the fixed one. And then I'm gonna use the first one, which is 0. Now, if you come up here and click away from it, it's gonna give it the address, but it don't give it the tag. If you hit enter, it's gonna ask you to assign it a symbol name, right? Now, if I forget and I want to do it a symbol name, then I can come up here and do what? Just right click on it, come down here and put what? Edit symbol, and I can give it a symbol. Give it a name. Now this, we call this a down drop. What I'm going to do is I'm going to take this push button. Don't pay any attention to this stuff on the bottom. That's just reference numbers. Here's the address. So notice what it did. It put the type of instruction it is. It put a colon, a 0, and then it puts the bit number below the guy itself. So what this does is that this is an output port. So if I had a light hooked up to output port 0, so here's output port 0. Okay. And here's switch 0. Here's switch 1. Okay. And these other ones that I'm playing around with, just going to get rid of them. Oops. Get rid of the rung. So to get rid of the rung, you can't get rid of the N. The N was put in there automatically, right? You understand? I'm going to come up here and check this. So we got two options up here. And that's what we're looking for. We're looking for all those E's to do what? Disappear. Can you see which one I clicked on? Either one of these will work. This identifies the whole file. This finds errors in the whole project. So if we were to come up here and make more ladder diagrams, it would come up here and do that for us. Normally this is the one we use right there. Now it doesn't mean that it is correct, right? You understand? So if I used output 4 and I wanted to use output 3, it can't find that. It don't know. All this means is that it's in the right syntax. Syntax is the correct way of writing in a language, right? Okay. So what I want to do now is I want to send this program over to my PLC. We call that a download. So over here, I'm going to click on this. I'm going to choose what? Download. Right now, and this is where you're going to give this guy a name. It's going to give you a default where it's going to save it at. If you wanted to put them on your USB thumb drive, then you could come up here and point it to that, right? Does that make sense? I'm going to put mine on the desktop. That way I can find them real easy. Give it a name. Then I'm going to save it. Then it's telling me it's going to do what? Downloading the program. By the way, this is not the title. This is the title of the CPU. We can actually give the processor a name. And it's telling me, do I want to switch it back into run mode? Change back to run mode. So notice what happened to L1 and L2. They both turned what? Green. Are we okay? Oh, my tags are not showing. Okay, here we go. So what I'm gonna do is, I'm gonna come over here and close the switch. And, it's not the one I wanted to close. This is the one I want to close. You see it turned green. It told me that that input is getting an input from that switch. So what's it waiting on? I got those labeled backwards. It's waiting for, okay. So I made a mistake. We'll come up here and go offline. So anytime you're going to change the program on this PLC, you have to go offline. Let's see, I did that. Yes or no? I want this guy to be right here. I want this guy to be right here. Check for errors. It says it's okay. What's next? Come up here and do what? Do what? Download. It's going to ask me for a revision number of the program. So if you don't give it, okay. So this is. So what we're going to do right now is, this is what we call the stop button. Okay, so right now I've got it true. Then I'm going to come up here and just touch the start button. Can you see what it did? So the light up here should be on for output 0. And then whatever I had connected on that guy would be energized, right, or it'd be running or whatever it's hooked up to this output. And this guy would run forever until we do what? Turn off the power. That's not exactly true for a PLC. A lot of PLCs have batteries in it, but go ahead. Yeah, so we do stop. Neutron button. So like I said, if I try to put, in a lot of these rules, if I come up here and break them, sorry, gotta get it in the right room. If I come over here and break them, immediately it comes up and says, well, I got an error. And even when I come up here and check it, it don't clear. What's going to happen if you check it and it's got an error, it's going to pop this up and tell you where the rung is. And it says I've got an invalid output instruction position. So what it's going to try to do is going to try to tell you where your problem is. Makes sense? So I just broke one of the rules. What did I try to do? Yeah, multiple loads in a line. So if we're going to use multiple loads, only thing we can, of course, it's also giving me 2 errors because I didn't assign this a lot. Address, yeah, very good. So that should do away with one of my errors. Yeah, so one of the errors said I hadn't assigned it an address, but this it says I have an invalid output instruction, right? I just fucked that up. So what do? It's going to come up and give me a watt, and then I'm going to come up here and this is the symbol for another rung, right? Can y'all see it up there? Yes or no?
Yes.
I'm gonna do what? Drag it down. It shows me where I can put it, right? Okay. By the way, we can have outputs without inputs, but we can't have, but every rung's got to have an output, right? So what's it waiting on? I got question marks up here. What is it waiting on? Address. Logic Pro emulates a 504, SLC 504.
What 504 mean?
That's just the CPU model number. So it's a 500 series, and then they got the 502, 501, so it's just a model number. So this is a 504 right here.
Probably said error code over line said error 504. That's right.
Oh, I could understand that. That's the problem with Allen Bradley or our Logic Pro. It don't give you the error. It gives you a number, and then you got to go up and look it up. So you type in, RS Logic. So this is so this up here in this process. We call this the project tree. That makes sense. And then these are all your instructions. These are your most used instructions. And then this would be the individual instructions. The only ones we're going to go get through is, in this class, is timers and counters. Of course, most of y'all know what a timer does. What does a timer do? Time, yeah. And then counters, they do what? This is the processor status files. And then this right here would be your errors. It just gives you a number, then you got to go in, you got to look it up and see what it is. We had one, when I first started teaching it, we had one that was popping up on the 504s. It was faulting and faulting and faulting. And I finally we couldn't figure out what it was. And Nancy said, well, there's no program in the PLC. So the PLC had been off so long, we don't have batteries in it that it lost its light. So it's got to have a program in there. So all we do is just download a dummy program in there and get it going. So sometimes the errors are hard to figure out. So the inputs, this is going to show us the status of the inputs. Can y'all see this? So let me So this shows me the status of the inputs. And notice when the switch is closed, can y'all see it? It gives me a 1. And then when the switch is open, you'll see what it's doing. So this is what the program looks at. It don't actually look at the switch. It looks at this data file right here. And it uses this to determine which switch is closed and which switch is open. And then the PLC examines it to determine what it considers to be true and what it considers to be false. So this one on the left, this is a normally open. So it's going to be true when that contact is closed. That makes sense? So we call that symbol right there, it's called an examine if closed. This symbol right here, this symbol right here is true if it's open. So this is the program. So if I wanted to change this, let me go offline. So the first thing I'm going to do when I create a new program is do what? Time the CPU. Good. And I can't put anything into this run. See that? And why is that? Good. Okay. So right here, I'm going to put change instruction type. And so what is it now? You see what it says? Okay. And so this is why you got to know that. So now if you wanted to change it, now it's going to change. It changed the symbol for me. You know, see that? So normally in the motor controls, and this gets people confused all the time that's gone through motor controls. So this is a symbol for a push button. This is a momentary contact push button. Notice it's on the bottom, right? Understand? So we call this guy here normally closed. Then I would come over here and I'll put this one up here. It's above the top. So this is going to be a normally open. Okay. And then I would come over here and I'm going to put a relay coil. And I'm going to give it a name. We'll give it a name. Okay. Then I can put the contacts that are controlled by that relay. What I would do is I would give it the same name. And this would be relay logic. Okay. I know these phones are very, very important to you, but I don't want y'all to be texting this stuff in my class. Now notice here so how would this work? CR1 comes in, seals in, and then how do we do the stop? Now notice here, this is a normally closed. Now why do we want to use a normally closed for a stop button?
Well, if it's open, you hadn't.
Yeah, if the switch opened, the system would stop, right? You understand? So this gets people, if I was going to do this same thing in the PLC, then this is going to, normally we'd say, okay, I'm going to program this in the PLC. I come up here, I use a contact, right? You understand? Now, what would be the problem with using that symbol right there? Well, no, it's not normally closed. In PLC, we don't call that normally closed. We call it examine if open. That would represent, so this would have an address, right? This would have an address. And then over here, I might assign this to an output. And then I would give this guy over here the same address, meaning that this contact is controlled by that guy right there. Now, this is an examine if closed. This is an examine if closed. This is an examine if open. So that means this would be true when the switch is what? Examine if open. So it means this guy right here is true if the switch is open. This says this is true if the contact is closed. Switch, we'll use switch. So that means to make this true over here, this guy's got to be true, then I've got to use the normally open push button. Yeah, now it's screwed up. Because if my circuit opens, I cannot stop my motor. I understand that. That's enough. Okay. So that means if I use a normally closed push button right here, if I come over here and I wire to my PLC, I wire a normally closed push button, this guy is going to be false, which means my motor would never, I couldn't complete this circuit right here, right? You understand that? Yes or no? Okay. So if I come over here on my program and I use that symbol right there, this thing says it's true when it's what? It's true when it's what? Open. So if I use a normally open if I use a normally closed contact, it means it's false. So to make this run, somebody's going to have to come over here and press this button over here, and they're going to have to press the start button, right? You understand? Yes or no? Y'all doing this, but I know. It's like those wobblehead dolls some people put in theirs.
We do it on them, but it's hard to walk.
Huh?
I'm doing it on them, but it's hard.
Well, this is the problem we have, is that this said, when it says examine if open, it means it's true when it's open. So the PLC, go ahead. Well, this is the actual physical switch that you have connected to the panel. Okay, so what I'm going to do over here on my simulation, I'm going to change that to a normally closed switch. Why do we want a normally closed switch to be a stop button? Well, the problem is that wires break all the time. So if a wire broke on that switch, would you want the motor to stop or would you want it to keep running? You want it to stop. Okay. So what I'm gonna do, and this is my stop button. Yeah, can you see this? I can't make this any bigger. So now. Yeah, the problem is that we won't, and this is, I don't forgot what law it is, or OSHA rule is. A stop button has to be a normally closed push button. These are the buttons that stop motors, right? You understand? Now, why do you want it to be normally closed? So if it breaks, the motor stops. Okay. So this is my stop button over here. I'm going to use this. I got the wrong address, guys, because this is, okay, so that's my stop button. Now in motor controls, it would be a normally closed push button. Yeah, so over there, that stop button is normally closed. But the problem is when I use this symbol right here, okay, let's change this to 0. Now notice what's happening. This is a normally closed push button, but it says it's true when it's open. But I'm using normally closed, so it's what? False. So I'm coming here all day long right here, and I'm pressing this and then nothing happens. If I change this to a normally open push button, now it says now I come over and press this button. Now it says it's true because it says examine if it's open. So now I'm using a normally open push button as a stop button. So what would happen if this wire broke coming into my PLC? It says examine if open. An open wire is just like an open push button. So if I use a normally open push button on my PLC and I call it a stop button, and the wire opens coming in there, I can't stop my motor. So notice it says I got normally open and it says it's true, right? You understand? So now I come over and push this button and everything seals in and it appears to work. But what's the problem? I'm using a normally open button as my stop button. So what would happen if that wire broke coming in on that stop button up there? It'd keep going because an open wire would be considered to be an open. Now, if this was motor controls, that would be a normally closed push button. In PLCs, though, what are we going to? We're not going to use a normally. We're not going to put an examine if open. We want it to be true when it's what? When it's closed. Good. So what I'm going to do, I'm going to take this offline. Then I'm going to change this to a examine if closed. I'm going to change this to a normally closed. So now it's true all the time, right? And this gets people every time. So now it's true because I'm putting in, I've got an examine if closed and the switch is what? Closed. So it says it's true. Okay, right? Now I can come up here and press this other examine if closed. Now notice when I press it, it becomes true. But as soon as I release it, it becomes false. But now I'm sealing in around there. Well, notice, I'm going to hit stop. This is my output right here. Okay. Now what I want to do is up here on my panel, I've got a start button and I press it. So if I want these lights to stay on there, what do I have to do? I have a switch and I have to leave it on. We don't like to do that a lot. We don't like to use a lot of switches out in control. We like to use a lot of push buttons, even if they're simulated on a HMI panel. So what do? You go over there and you just touch the start and then you let it go. Right? You understand? So what happens, notice that right now, this guy right here is not made because it's being controlled by what? By this guy right here. See that? So I'm going to come here and press that one. When I pressed it, the bottom one makes, and now what I can do is I can release that button and it seals itself in because it's holding itself in. People call this a sealing circuit. They call it a memory circuit. So it's got different names. They call it a 3-wire circuit because it's got 1, 2, 3 wire numbers between here and the load. So some people call this a 3-wire control. But we call this the seal in because what it's doing is holding that relay in, right? You understand? So it's a good question. So that means a stop button, we have to use an examine if closed, which this is big difference. This is big difference from motor control. Because motor controls, I would use a normally closed push button. But then you get in here, and this guy in the book does the same way. He'll use a normally closed symbol. He'll use the examine if open or a stop button. We got to be really, really careful with that when you go back in this book because it's going to do it wrong, right? So now, if my input, if that wire that's connecting my push button to my input port, if it opens, then it says examine if closed. Now it goes open and the motor would stop. It would drop out like this. So y'all seen these start-stop stations, right? Just about anywhere you work that's got motors. You do what? You get a start. Either it might be on an HMI panel, but it works exactly like this, guys. You hit the start, and then when you want it to stop, you either do it with sensors or you hit a stop button. And this is the way it works. So these symbols are called examine if what? Not these. Yeah, it's opposite of what the symbol says because that means I have to press the button, right? So these are examine if closed. These are examine if closed. And if it's got the slash to it, those are examine if closed.
When was that did you touch something and it brought up a block had to eat, so here,
Yeah, well, what I did is I came up here and I'm gonna go offline and we can do some editing on offline. And this is a little different. What I can do here, instead of me trying to find it, instead of me coming up here and deleting this and then pulling out another contact, we have the ability to right click on it and then we can edit it. And notice what I did. See what I'm talking about? Yes or no?
well, I just thought, oh, maybe you wrote that in.
Well, you do on RS Logic 500. This is not RS Logic 500. This is a simulator, right? You understand that? So yeah, on the real one, I had to type it in. I had to change the C
Okay,
to
I
an.
just remember doing that
Yeah.
somewhere.
So this is not exactly right. This is this is a really good program, and I'm really impressed the number of programs that I've written. How much this guy had to go to get all the graphics and everything right. But he does have some problems. Go ahead.
It's on the App Store, you know.
No. You'll have to go. And I don't know if you can get it for a tablet or not. I don't know if it's available for an Android. It's a company called Learning Pit. Huh?
I know the name. Get your iPad. It's on Apple.
No, it's not. This is a computer application, so you'd have to have a laptop. Probably a compatible. You could use an Apple.
Oh, it's on the same way. Yeah, that one. I know it. But we don't need it. You don't have to.
No, but it's really good to practice. So what you can do is we had some and it used to come with a version in the textbook, but you had to have the CD in there to run it. You couldn't just run it like I'm running here. I've licensed mine. But they the textbook company basically did away with it. But what we would have is we'd have people, they'd look at their labs and they would come up with the circuit this way, and then they'd come in, and then all they'd have to do is just program it into the PLC. So the way the labs are set up, if you look at the lab book and you get into the labs on the actual computer, on the labs, it's one set of labs is for the PLC. The next lab is for Logic Pro, and they're exactly the same lab. And why they did that, I don't know. Just to make the lab book real thick, I think. But because some schools can teach PLCs without having PLCs. So what they do is they use this simulator right here. They can teach the PLC, but still, it's still not exactly the same, right? There's no way in the world you can wire up this simulator on this guy here. You would have to learn how to wire it. So everybody got their lab book? Really? Everybody got
I'm working on that. I wouldn't talk to the book.
So let's look at the first lab. And I can run off the first 3 labs for you, Karen, but that's it, okay? So that's why I was asking, because I'll have to run some off. We're legal as far as running off those 3 labs, but we can't run off any more than that for you. Just the first 3.
Yeah.
We can't put any more than that up there, right? You understand that?
Yes or no?
So what we have is we have these guys down there. So anytime you talk about the SLC 500, these are the PLCs you find. These are not the ones we're going to use in class because the interface in it is so slow. It's using RS-232. The interface that we're using is called a RS-485. It's also called a DH Plus, which is pretty fast. We'll see that when you put it on monitor. So what was happening on this PLC is you'd flip a switch. If you flipped it real fast, it would never have time to send that information back into your computer for it to light up. The PLC was real fast. We're gonna pair up. So we got one person that's not here, so one person will be by themselves today. So we'll pair up in twos. We don't want more than 2 people on a PLC. And what we're going to do on the first lab is we're just going to look over the PLC and we're going to see what they have. By the way, on these, if you're on the station assigned to this PLC, this is not the number of inputs and these are not the number of outputs. The number of inputs that your PLC has, the number of outputs PLCs, you have to look at the PLC. This is just a mount that we mount the PLC on and then we wire it up, right? Understand? That makes sense? So So we had the problem we had, people got on this last semester and they said it had 16 inputs and 16 outputs. And I knew right off the bat that they were looking at what? They were looking at the mount and not the what? Not the actual PLC itself, right? So we have the 1100s. And then we have the 1000s, these are the little suitcase PLCs. Huh? So these are going to be your trainers, right? And of course it says what type of PLC is simulated by the Logic Pro. That's a, what? I just told y'all. Huh? No, that's the interface.
500?
Yeah, it's the 504. The CPU, where are you going to get the CPU information on your PLC?
On the side.
On the side, right? This guy's pretty easy to see.
Yeah, that won't happen.
This one is going to be on the door, but nobody's going to be assigned these PLCs. You're either going to be on 1100 or you're going to be on the 1000. The 1000 is a true fixed PLC. This guy is what I call a hybrid PLC. It comes with some fixed ports, but then you can mount